Right, so we all have our worksheet 11. We're going to talk about one of my favorite topics today. I like these because they kind of incorporate everything that we've done in this chapter, and most of all, I like them because they're application problems, and I can finally tell you somebody uses something we do. Okay, warm up here. SAT question. What would you do first? Get it all on one side. Yeah, my usual trouble with my cursor here. SAT, I really encourage you to look at the choices right away too. Just because this is making me think there might be two solutions, huh? Okay. All right. If we add 2x squared over here, be careful, it's not going to go away, right? It's going to make 4x squared. Then what else do you want to do? Maybe put this over here and then divide. Any reason we can't have two solutions? Not that I can think of, right? All right. What we are doing today is linear programming. Many applications in business and economics involve optimization, finding a minimum cost or a maximum profit or minimum time to make something, or finding constraints in which we can get the maximum productivity, etc. So maxes and mins. And when the quantity to be optimized, it can be represented as a linear function. It's called linear programming. We're going to talk about what's called an objective function, and we're going to talk about the constraints. All right? We're going to come back to this in a minute. We're going to look at 12a and do a little puzzle first. Okay, an objective function, the constraints, and the feasible solutions. That's all the vocabulary we need to get good at, but we're going to look at this puzzle first because it's easy. We can try this, okay? It says, What's Up Toys is a small toy company that specializes in toy cars and trucks. The people at What's Up Toys are confident they can sell all the toy cars and trucks that they can possibly make. But there are two constraints that limit their production today. Each car that they make needs 4 wheels, each truck needs 6 wheels, and they only have 360 wheels in stock. Okay, each car needs 2 seats and each truck needs 1 seat, but they only have 100 seats in stock. All right, they helped us out. They said we should let X be cars and Y be trucks. Can anybody come up with a constraint or an equation we could use to limit anything here? Look at you guys go. 4 wheels per car plus 6 wheels per truck has to be less than or equal to 360 wheels. Is that where we're at? Okay, and what about seats? 2 per car plus 1 per truck has to be less than or equal to 100. I didn't write one above the other for any reason. I just started down kind of low. So, all right. There are what's called hidden constraints, meaning there's 2 constraints that we didn't write an equation for, and that would be that we can't have negative of either one of those. Does that make sense? Can't make negative trucks or negative cars, so these constraints apply as well. All right, so what we're going to do is we're going to graph these. And remember, inequalities mean we're going to do some shading. All right. They did the hidden ones for us already, right? They left off all the negative jazz. Okay, can anybody remind me what the equations were? Less than or equal to 360? Okay. You can get this in slope intercept if you want. I kind of like, do you remember like the first day of class I talked about finding the zeros? These both go into 360, right? So if I put a 0 in as x it'll say 6y equals 360. 360 divided by 6 would be 60. So that's one of the intercepts. If y is 0, what will the equation say? 4x equals 360. 360 divided by 4 would be 90. Okay. So over 0 up 60. Over 90 and up 0. I'll use this because it's blue, I guess. There's our line. The other equation, anybody reminded me? Okay, I didn't talk about shading. Where should we have shaded for the blue one? Right? Anything in here we could make. Yes, everybody understands that? We could make 10 and 30, we could make 50 and 20. Okay, so anything in here we could feasibly make. We'd have enough. What was that one? Tires? Wheels? Wheels? Okay. Maybe it would be easier to do this one by slope intercept because all we got to do is move that over. I don't know. We got it. Y by itself starts at 100 down 2 and over 1. As long as the scale is the same on both, we can do down 2 boxes and over 1 because it's down 20 and over 10. That's the same. Thanks. Yep. Didn't say I could count. I was like, it can't turn out like that. Okay. Does it make sense that the other intercept is 50, guys? 2 times 50. 2 would go into 100, give 50. Okay. Under or over that one? Still, they're both less than, right? Okay, so the feasible region, do you remember that vocabulary? Is all of the area in here. We can make any set of tire or any set of cars and trucks we want as long as it fits in this region. We could make 20 of each. Okay, we could make 10 of each. The premise of this linear programming is that any maximum or minimum for an objective function will occur at a corner point. Okay? If we wanted to find the minimum amount of time needed, guess which corner point it would be at? We'd make 0 of everything, right? Okay. But if we want to use this sentence, it says, suppose the profit on each toy car or toy truck is $1. Okay, we make $1 for each. How many should we make in order to maximize the profit? So it will always occur at a corner point. So you have to find those vertices or corners. What is the ordered pair for this corner? 0, 60, 0, 0, 50, 0. Be really careful. I get those backwards all the time. And this one, can we tell? We're pretty confident it's 30, 40. How could we double check that? You could plug it into both equations and make sure it works, right? That'd be 120 and 240 is 360. And that would be 60 plus 40 is 100. When it's more complicated and you can't tell where they intersect, could you solve by elimination those two equations? Could you solve by substitution? Could you do a matrix and do either RREF or 2 matrices and do an inverse to find the point of intersection? You guys are geniuses. You can do any of those things to find that point of intersection. We were really lazy and said we can clearly tell from the graph, right? All right. If we make $1 each, how much are we going to make at this corner? $60. How much are we going to make at this corner? $70. How much are we going to make at this corner? $50. $0. So the maximum profit would occur 30/40. Why is it not 40/30? Okay. Why doesn't it fit on there? Can anybody go back to the problem and tell me why we can't make 40 and 30? We don't have enough something. 40, not enough seats? Okay, you guys quicker than me. If you made 40 cars, they each take 2 and 30 seats in the, so that would be 110. We don't have that many seats, right? All right, back to the question. So where would the maximum profit occur? 30 cars and 70 trucks, and our profit would be? Yeah, 40. Thanks for catching me. Maximum profit was $70, right? Okay. What happens though if we change the profit to $2 on a car and $4 on a truck? Is that going to necessarily stay at the same points? What did we change it to? I forgot already. Okay, we need to write what's called the objective function or the profit function. Okay, the objective function. What did we just say it was? I forgot already. $2 per car, $4 per truck. Okay, so if we put this one in, we'd get 240, yes. We put in here, we'd get 60 plus 160, which is 220. Down here, we'd get 100, and here we'd get 0. So changing our function, our profit margin, changed to we'd need to make only trucks. We'd use all our tires for trucks. We'd have extra seats, I think. Yes? Okay. So we would make, what did we just say? 60 trucks only, which would make us $240. Okay. So you can't assume which corner is going to work. It depends on the objective function you're putting it into. That's what I was trying to show you there. Everybody good? Okay, let's go back to worksheet 11. You just did a problem that's on your homework, by the way. You got part of the homework check done. All right, so back here. Did anybody get what the objective function is? It's at the end of the problem what we want to maximize or minimize. Okay, it's not one of the things we graphed. What were the things we graphed? They were the inequalities called the constraint. Okay, this is what we were optimizing at the end, was the objective function. And the feasible solutions are just all of the things in our shaded area. All right, little vocabulary lesson there, okay? This theorem says problem can be optimized. It will occur at one of the vertices of the region. We got that? Okay. This says you should graph and shade, find all the vertices, and then use the objective function. We are so on top of this. Our learning objectives are today. For the quiz, you need to be able to write an objective function and a system of linear constraints. You need to be able to graph the feasibility region and find all the vertices. Okay. And then find the maximum as well. I don't know, is that on this slide? I can evaluate the objective function to find the maximum or minimum. Look at me. Okay. All right, so what are we going to do here? It says find the maximum and minimum values for what values of x and y they occur and what values they occur at, subject to the given constraints. Okay. X is greater than 0, y is greater than 0, means it's in the first quadrant. We're done with those. What do you know? Okay. How do you want to do this equation that I'm going to do in red right here? Want to get it in y equals form, or do you want to find the zeros? Okay. If you get it in y equals, it'll say less than or equal to negative 2x plus 10. Anybody tell me what the other 0 would be? Yep. I'm going to draw mine badly, kind of on purpose, because I'd like us to have to figure out where they intersect other than by graphing. All right. Can I do the other one the other way? You can get it in y equals form if you want. Am I shading above or below that one? By the way, it's not always below. Okay? It's not always below. There's times when we want to minimize the cost of something. So we could go above and above and above, but we want to find a minimum cost or something. So, all right, what about the zeros for this one? Can anybody help me? If x was 0, y would be, in order to get it equal to 8. If y was 0, then this would just say x equals 8. So 4 and 8. All right. I said I was going to graph them really crummy, and I did, but it still looks like they intersect right there, but maybe I'm wrong. How could we solve? Can we just review real quick? Could we put this in a matrix to find where those two equations intersect? It's kind of a time-consuming for this particular problem, probably, but what would it look like? Which way do you want to do it? One matrix or two? One? So I'm going to go to matrix A, edit, and what size would it be? I only want to find where these two intersect. A 2 by 3. And what are my coefficients? 2, 1, 10, 1, 2, 8. And since I put it all in one, I want to do what? RREF, which I might already have on here. Well, I don't have the right matrix. Anybody get 104012? What does that mean again? This means x, this means y, so this is 1x equals 4 and 1y equals 2. Everybody's good? Okay. So did my graph get way better than I thought I did when I found this point right here? Yep. Okay. I still don't have all my corners listed though. The feasible region is under the green line and under the red line, so I'm down in this little corner because they were both less thans. But what are all my corners? I got 0, 0. You get a freebie on that one. Over 0 and up 4. 5. Over 5 and up 0. And then 4, 2. Okay. It said to find the maximum and minimum value, and they gave us this objective function, okay? So 0, 0 is going to be the minimum. What do you think? I actually think you're wrong. Because it says minus, right? 0 might, okay. So let's put all the values into the function. Doesn't that seem like the easiest thing to do? We put in 0, 0, we get 0. If we put in 0, 4, we get out what though? Negative 8. If we put in 4, 2, we'd get 12 minus 4 is positive 8. Did I do that right? Put in 5, 0, we'd get out 15. Normally, I'm thinking if there was a plus in there, definitely it would be at 0, 0, the minimum. But because it was minus, the minimum value of negative 8 occurred at 0, 4. And the maximum of positive 15 occurred at 5, 0. Does that seem right, guys? And that's kind of how I wrote it on the quiz. I made it like a profit sentence, and I wrote maximum profit of blank dollars occurs at blank, okay? And you get one on the quiz where I've done it all for you, and all you have to do is maximize it, because I just want to know that It's easier for me when I'm grading based on your understanding of the concept if you don't have to do all the parts at once. Does that make sense? So there's one problem where you have to find the corner points, one problem where I gave you the corner points and you have to maximize the objective function, and there's another question where you have to write the equations and not actually do it. So I broke it down into pieces so I can tell what it is you don't understand if you don't understand something. All right, do we need to do this one? Want to do this one together or want to go on and do an application? Do it again? Okay. What about this guy? Where are the corners for this guy? What makes 4? 0 plus 4 or 4 plus 0? And it's a less than again, so it's this little tiny corner. Okay. What about this one? If x is 0, y would have to be what to make 6? 2. And if y was 0, x would be 6. Okay. I'm pretty sure my graph isn't good this time. I have this little region down here and I can't even tell how many corners it has because I graphed it so badly. I think they do intersect though, right? Can I be lazy and do this? I have 1x plus 4y. Just kidding. Right now, the top equation says 1x plus 1y equals 4, right? The bottom equation, if I multiply it by a negative, then I can just add them. I got y is 1, so if I plug 1 back in, I'd have x plus 1 equals 4, x equals 3. Anybody do a nicer job than me and find 3, 1 is that? Are you kidding? So they were supposed to intersect over here? Oh, yeah, clearly. So what are we using, folks? The big dot theorem. Okay. They intersect at 3, 1. I'm thinking then that this is 4, 0 is a constraint right there. That should have been like that, yes? Mine is so bad. And 0, 0 and 0, 2. Is that what someone has who did a better job than me?
Yes.
I think it's kind of like going like this a little bit, right? Is that what yours looks like? Okay, anyway, don't make fun of me. Okay, we're putting those into this function up here. So 0, 2 would give me, anybody? 4. 3, 1 would give me 5. 4 and 0. So our minimum occurs minimum of 0 at, I don't care which way you write it, but 0, 0, and a maximum of 5 at 3, 1. We good? Okay, now let's play around with another application. A leather company wants to add belts and wallets to its production line. Belts require 2 hours of cutting time and 6 hours of sewing time. Wallets require 3 hours of cutting time and 3 hours of sewing time. The cutting machine is available 12 hours a week and the sewing machine is available 18 hours a week. Belts will net $18 in profit and wallets will net $12 in profit. How many of each product should be produced to achieve maximum profit? Okay, I have to tell you that these can be very confusing because there are so many numbers in there, right? This is just me, but I always write that objective function, the profit sentence, because I can usually pick that out pretty easy. It's got the dollar signs. Sometimes other ones have dollar signs too, but if I can pick that out, then I know I don't need those numbers anymore. Okay, and get those out of the way. So what is the profit sentence here? If we let X be belts, okay, that's always the first thing you do is figure out what we're actually talking about. And Y be wallets. What is the profit we make on a belt? Belts will net $18 in profit. And wallets will net 12. Okay, now we're done with that sentence, guys. We can stop looking at that one. And now there's a whole bunch of stuff about belts require 2 hours of cutting and 6 hours of sewing. Wallets require 3 hours of cutting. But the thing that cuts us off or that sets a restriction is the cutting machine's only available 12 hours a week, right? So we have to have something is less than 12 that has to do with cutting. Well, 2 hours of cutting for a belt. So that's what? 2 per belt. And cutting for the wallet is plus 3Y. Okay. Sewing time. Well, we only have 18 hours available of the sewing, so it's got to be less than or equal to 18. But 6 hours of sewing for every time we make a belt, so that would be 6 per belt. And 3 hours per sewing. No, what are we doing? We're sewing 3 for sewing wallet, right? Okay. Everybody all right? A lot of numbers and letters and things to think about in there. Okay. It's all graphed for us. They even found the intersection point. How could we have found that intersection point? Guide me through that. We could do a, well, you could get them equal to Y and graph it on your calculator and find the intersection, but that doesn't sound that fun to me to get them equal to Y. You could do a matrix, right? Could you just do elimination because the 3's match up? Okay. Yeah. All right. They did it for us. We're going to go with it. And then they put all their corner points into the objective function, and they found that the maximum profit resulted in 1.5 and 3. Is that a reasonable answer? It depends. It says 1.5 belts for every 3 wallets per week. You get halfway through it and make it the next week. If that, it was significantly more profit to do that, right? So maybe it does make sense. Sometimes it isn't just the whole number of answers. Okay. Yeah, I don't think it's a. All right. Linear programming models can have one multiple or no optimal solution. If the graph of the objective function to be optimized coincides with the one side of the region, then anything on that line would work. Okay? So if the profit function actually was one, if all the points on that line could work, if it was, we're not going to have any like this, but it's possible that you can have more than one solution. Actually, I think on the back of the puzzle, the bakery box question you have on the back of worksheet 12, I think there might be 2 points that give you the maximum, okay? You get the same equation, you get the same value for profit at 2 different places on that one. All right, if a region doesn't form a polygon, but instead an unbounded region, you can have no max or min. We're going to do one tomorrow where we have a situation like this, okay? Everything above here is feasible, and everything above here is feasible. So your region of bounded is going to be like this, and it's unbounded because everything up here, well, if we want to minimize cost, we have to decide, does the minimum cost occur at this corner, or this corner, okay? If we wanted to maximize something, guess what? It wouldn't happen because it's unbounded and goes up forever. All right. Do we need to do this one? It's pretty much all done, right? You just plug it in. We've been doing these already. We're so far ahead of this. Let's skip this. Ooh, interesting. Should we try this one? Okay. What's the objective function here? Yeah, this guy. We're not graphing this guy, right? Oh, but notice that coincides maybe with this. I don't know. 2x plus y equals 11. We'll see what happens. Okay. Maybe we should graph all these other guys first. There's some crazy business. The x's have to be, x's are which way? X equations. Up and down. So between 0 and 5. So x is in here somewhere. Okay? Between the y-axis and 5. That's these two. I just didn't bother to put a red line over the top of this. All right, what about the y's? Which means above the x-axis and below the line 5 here. Okay, I should have probably kept going here because we really don't know that it can't be negative. Okay, what else do we know? Well, we're down actually to this little square here now, right? Because it's got to work in the red and the green. All right, so I'm going to use blue to graph this line. How do you want me to do that? Negative 2x plus 11, like that? Okay, down to... So when I go below that, are you getting this little 5-sided region maybe in here? There's a really short little side over here too, right? I think it looks like this. Anybody else get something that looked like that? All right, so this corner right here is what point? Over 0, up 5. 0, 0. I'm doing the easy ones. What's this corner down here? 5, 0. All right. This one, what do I know about this one right here? This corner, guys. It's on what line? It's on y equals 5, and it's on this blue one, negative 2x plus 11, right? If it's on y equals 5, what has to be true there? The y value has to be 5. So if I go back to the original equation and I plug in y equals 5, x is 3. You guys could probably tell on your graph. Did it look like 3, 5? Mine's just such a mess. I'm trying to make sure I do it algebraically. All right. And this line over here was on the up and down red line, which meant what? X is 5. So if I go back to my blue equation and I put in x is 5, I get 1. Everybody already have those? Am I the one taking forever? Okay. Now we got to put them all in this guy. 2x. You know what they do is they make a little chart. They list them all. 0, 0, 0, 5, 3, 5. Seems like a lot of work, huh? 5, 1, 5, 0. And then they put them all into, what was our equation? 2x plus y? Well, this one's going to be 0. This one's going to be 5. That's going to be 2 times 3 plus 5 is 11. 2 times 5 plus 1 is also 11. Did someone get that? Okay, so the minimum of 0 occurs at 0, 0. And the maximum of 11. Now, yes, I think it actually occurs not only at 3, 5, and 5, 1, but any points in between those would also work on that line. Okay, so Isaac tried 4, 3, and it worked as well. So it's maximum of 11 occurs on the line 2x plus y, anywhere between x, I don't know, just all points in there. Can we just leave it at that? Because I'm going to put this on the quiz. I'm not going to ask you to word it that way. Yeah, between, well, let's list our endpoints. How's that? They were 3, 5, and 5, 1. Is that right? Anything on the, all right. I'm not going to ask you that on the quiz, I promise. All right, we got time to do one more application. Okay. Skating. This one is kind of set up for us, I think. What's the objective function? Okay. It looks like over here they have skates are x. Do you see how they set it up for us? It says the x-axis is roller skates. Oh, not just skates. Okay. X equals roller skates and y equals ice skates. All right. What is our profit? Okay. That's our profit. You can write f of x. Yeah, whatever. Now we got those numbers out of the way. All right. We have constraints related to assembling. We only have 200 minutes to assemble, so we have to be less than or equal to. And every time we make a pair of roller skates, it takes 5. And every time we make ice skates, it takes 4. So 5x plus 4y is got to be less than 200. Okay, can we graph that one? If you put in x equals 0, you'd have 200 divided by 4, which would be 50. If you put in 0 for y, you'd have 5x equals 200. 200 divided by 5 would be 40. Okay. Then our other constraint that I'll do in blue is we only have 120 minutes of packaging time available. Every time we make roller skates, we can throw those puppies in the packaging for how long? 1 minute it takes us. But the ice skates, we have to make sure we don't cut ourselves, so it takes us 4 minutes to package those. Okay. Where are the intercepts for that one? 0. If x is 0, y would be 30. And if y was 0, it would say 120, which doesn't fit. That's not so helpful. Over 0 and up 30. Okay. How about we find another point on there, or the slope? If you put in a 40, that does, yes, 40, 20 works. Is that right? If you put in a 40 here, subtract it would be 80 divided by 4 is 20. So 40, 20 works just for one more point to put on there. It does have a negative 1/4 slope as well if you solve for y. Okay, my line is horrible. I'm pretty sure they don't intersect there. If they do, it's... Okay, they don't intersect at a nice place at all. Okay, so how could we find the point of intersection? Look how nicely these drive. Look how nicely they line up. You want to use a matrix? We can use a matrix. But can't we just subtract? If we just subtract, we'd get 4x equals 80. X equals 20. Why is that coming out nice? If we put in a 20, For x, we get 100. Subtract, we get 100. I get 20, 25. Oh, it's just not nice on our graph paper. I got the intersection is 20, 25. Anybody do a matrix? Okay. Where else are our intersection points, though? Or our corner points, I should say. 20, 25 is this one. 0, 30, and 40, 0, and 0, 0. Somehow I don't think our profit is going to be very good at 0, 0. Okay, we want to maximize our profit. So 30x plus 40y. 0, 0 would give us 0. 0, 30 would give us how much, guys? 120. 40, 0 would also be 120. And 20, 25 would give us 30 times 20 plus 40 times 25. This needs more zeros. Aren't these 1200? Thanks. And this one is 600 plus, is it 1600? Okay. I don't multiply well. It's not a requirement. Okay, so what is the maximum profit? $1,600 if we make what? 20 roller and 25 ice skates. We rocking this? Okay. I got news. Kind of exciting news. You have only 4 homework questions. Number 3, 9, and 29 on the book page. And that's why I gave you graph paper, because you're going to want to use nice graph paper to do those 3, okay? It was back there. And then on worksheet 12, you need to finish that up. So we did one side, you got to do the other side. That wasn't the good news. The good news is that's the last topic of the semester. I've taught you everything you need to know.